Hello, dear internet. So today there will be another scientific stream, another about the same topic about dimensional materials with special properties. And that's the first stream which will be separated by several parts because that's a big article, and I was trying to understand this article for a long time actually. Oh, it's very hard to even calculate how much time it took to me to prepare this article to some extent. And still, unfortunately, I have prepared it only for 70%. That's how I evaluate it. But again, that's the challenge for me to do my best on my own and then present what I have done best on my own, not to use something else. And another reason is that, of course, there is not so much things that I can use else, because that's how science works. There are some specialists somewhere in the world, and it's not clear how to reach them. Maybe it's possible to go to conferences, but still, no one will educate you, so you need to educate yourself on your own. And that's the goal of this actually project, to develop an app that will be used to productive personal studies and personal research. So that's constant test of myself and this app. If I'm able to understand more each week of something new, and later it will convert to my own research, but to do a good research in it, to understand well the very cited papers which explain what has been already done in the field. And okay, let's finally jump into the preview of the paper. So the paper is called On the Origin of Charge Density Waves in Selected Layer. Oh, sorry for this. In Selected Layer Transitional Metal Dichalcogenides. That's a review paper. It has 25 pages, but some of them are for literature, so real pages are around 21. And I forgot, unfortunately, to open it. Oh, that's my bad preparation. No, I didn't forget, it's just in another tab. So here is this paper that we are going to discuss. And also I forgot to say that I have a new camera, so the resolution right now is way better, and I hope that sound is also better. Maybe in some years I will watch this video again and at least reflect on the quality of the information. So today it will be for approximately an hour, and also I forgot to say that the internet here is not stable, so if I disconnect, then I will reconnect through mobile phone. So that's this article, around 22 pages totally, if we look just on the article, not on the literature. And let's finally open the best app currently existing for science. If there were some better apps, I would use something better, but I don't know any app which is better than this one, even though it's not developed. So that's the Rossnagel's paper, which was rewritten by me, of course, for my personal use, to fix what I understand and fix what I don't understand. Okay, yeah, let's maybe do like this and start our stream again in this beautiful format, which I enjoy a lot, where I discuss what is the most important thing which happens in this paper, and on the end we will dive into paper. And of course, if we discuss paper for 5 pages for 3 hours, then it means that it will take really a lot of time. That's why I also decided to do a stream today, because even though the internet is bad, like, I mean, it was bad during the day, I hope right now it will not be bad. That's also a motivation to do the stream today, because maybe tomorrow and the day after tomorrow will be not enough to finish discussion of the stream. So, of this article, I mean. Rossnagel, I mean, of course, that's a very high quality article. it was written by a person who was thinking about these topics at least for a year, because it would take really long time to be really familiar with a lot of effects, a lot of experiments, and a lot of theoretical works in this field. So it's a very big job to really dive such deep and collect a lot of experimental results and features of theoretical models, and also reflect on possibilities of applications of different models. So that's why there are a lot of there is a lot of information there, and of course it's impossible to discuss everything during one stream. And also, even at this moment, I have went only through 70% of this article, and not, I mean, I need some hours for extra preparation. But even now, I can guess what is the main idea of this article. So the main idea is that there are such special materials which are called transitional metal Dichalcogenides. And okay, I can even show you an image which I can also open here, but I'm not sure where it is. Yeah, so look how to use my beautiful app. If you want to open something here, you just click like this. And okay, there is a little question about, I need to close this thing. And if synchronization works, then yeah, we immediately see what we want. We don't need to scroll down, scroll up. That's another advantage of my app. And wait for a moment. So I wanted to open you illustration of how these materials look like, and unfortunately it's not very informative, just some balls that are connected in a special way. But the idea is that they are layered, they're two-dimensional, but something happens in 3 dimensions. I haven't actually thought really long, I mean, haven't ever thought for a long time about this configuration, but okay, maybe this discussion goes beyond this article. This article is big itself. So these are the special materials, and here in this article it's not written why exactly in these materials, yes, that's the beginning of this article, why exactly in these materials there are these special properties that they're discussed here, but at least a lot of models are proposed and a lot of effects are known and a lot of quantities are measured. So maybe at the last third of the article there are some comments about why exactly in these materials. But in the first, how to say, order of understanding, we can think about these materials as just some materials where everything that will be discussed during the stream is applicable. And why they're interested, of course, you can remember from my previous stream discussion of fast memory devices, or like simulation on quantum computer, which is a great improvement for quantum computation, but in terms of physics it doesn't give us much right now. So here they don't discuss applications, they just discuss physics. And in terms of physics, there are different effects, and that's why there are a lot of questions why one effect occurs, or why if we change a parameter then we get a transition from one effect to another effect. And you can measure the same effect from different in different ways. You can use STS measurement, like tip of a microscope, and scan through material, which was done, for example, in the previous stream. Oh no, not the one before previous one. The previous one was about oh yeah, well, actually in the previous also stream there was a comparison of some strange calculations using dynamic line field theory, and also measurement of derivative of a current through a domain wall. Okay, a quick reminder, that's also the summary of the previous stream. I just need to remember, yeah, so where to scroll, up or down, but I guessed correctly down. So that was from the previous stream. There was exactly the same material as in this family of materials. I mean, tantalum disulfide, which is the most famous material, and also in this paper, this material plays maybe the most important role. However, there are three materials that I discussed, so I'm not sure which is the most important out of these three. Maybe still this one. So that's what you can remember from the previous stream, that they scanned through the main wall, they measured current, and then did some very advanced and strange calculation using DMFT, and got some plots that could be somehow compared with what was measured. Okay, that's exactly what I mean. This was somehow measured, this was somehow calculated, and nothing was discussed about consistency of these results. But of course, there are a lot of things that happened there, and I haven't discussed this article with anyone. I haven't thought actually about this article after I did the stream and after I wrote my questions that arise. And also today, by the way, I have a place where I can write my questions and not be distracted to some paper. And again, I expect that there will be a lot of questions. So what I was speaking about, that's the summary of this article. So there are such materials. There are several effects that occur, and okay, right now on the top of my head, I don't remember any effects except ARPES measurement. And ARPES is, I guess, what's here, but here I didn't copy the caption to the plots. But so if I'm not wrong, then this is the plot that was obtained by some ARPES. And unfortunately, I haven't studied yet what is ARPES. For me, it's just some experimental method that gives us some information about energy bands, and then a lot of things happen here in this article because of energy bands. I mean, like if we have a new phase, then there is a manifestation of this new phase in energy bands. Yeah, and ARPES is the main here experimental method for measuring energy bands. So there are these materials. There is a phenomena which is called charge density wave, and unfortunately I didn't copy. Okay, I should read this note for myself. Okay, I will copy this image later because I could have opened it just by little scrolling, but I would need to scroll slightly more. I just do like this and do like this. I also need a little bit to move this little bit upper. So see, like that's the big advantage. I don't need to scroll finally. And also, by the way, I got idea about this app that I can create a function, like programming function that will display formulas. So look, some people say like we use this formula, like this formula 9, and what would you need? You would need to scroll and search for this formula 9 if links do not work. If links do work, then you will click and you will jump to another part of PDF. You will need to scroll back. Here you will be able to just press one button and it will insert all the formulas. So that hasn't ever done yet, hasn't ever been done yet. No one was doing this, but this project and I we are thinking about it, how to make framework really productive. So if you like it, then please like button and write in comments that you like it. Personally, I myself like it really a lot because I can just understand formulas without scrolling, and that's like huge improvement for productivity. So what I wanted to say is that So what is a charge density wave? Basically, that's the same modulation that you remember from my previous stream. So how does it work? That if we work in special pressure and special temperature, and I mean, you can ask me what is the pressure and temperature, and that moves us to the first stream ever done on this channel about articles, and that's this famous phase diagram. So I mean, like, pressure should be somewhere here at these values of gigapascal, so maybe not so very big, but also not so little. And I forgot on top of my head what is the value of atmospheric pressure. It's in pascals. I mean, maybe atmospheric pressure is somewhere here, but I could be wrong because I wasn't thinking about it for a long time. So if we work at this region, then some people say that we have a polaronic lattice, some people say that there is a charge density wave lattice. But currently, I haven't ever read a paper that would like argue that it's exactly a polaronic or charge density wave lattice. Actually, I got idea about improvement of the app, and I need to write it. Yeah, so see, like, I was a little bit stuck here because when this PDF goes for the full screen, I was trying to zoom out, but it wasn't zooming out, it was just scrolling the PDF. So that's another improvement that I should add to the list of improvements. So here, basically, the title is very similar to the title. I mean, title is different, but from this title, you can write approximately this image, but here they focused on the transition from one state to another. Here, they focus on more theoretical discussion of effects, I mean, of models, criteria of applicability and effects and other measurements. But basically this work also fits very well into this title. Oh, okay, but no, it doesn't fit because there is an on the origin. This phrase is here. And so yeah, that's because this paper tries to give explanation about why does this state occur, and also, okay, it has a lot of experimental results which do not fit this phrase on the origin, but they're very useful. I mean, maybe they're very useful because at least they look like a very nice summary. And let's a little bit scroll to the main pictures and main formulas from the article. And right now, of course, I'm not prepared to discuss main features and main formulas because, as I said, I didn't work out this full article. I went only through 70% of its information, but even this took me definitely more than 14 or 15 hours. Yeah, but I will finish this article this week. That's the goal. So this article focuses mostly on these three materials: tantalum disulfide, tantalum diselenide, and titanium diselenide. I have tried to understand why exactly these materials are so important, and exactly in them there is this peculiar physics, but I haven't reached this understanding, and maybe that's the open question for science. But okay, so here you can see the real like top view of this material. So you should think about these materials as two-dimensional materials. Actually, here this is written exactly what I'm telling you. So it's not clear for me how exactly motion in between layers affects the electrons and some physics. So we should imagine them as two-dimensional materials unless something happens, and they will start talking about properties of perpendicular direction, and this was at least in one place in this article, but nearly all the time we consider them just as two-dimensional materials. But also there are a lot of course, theoretical works about to develop theory for it, and I was just introduced to these works from this article, so I can't comment you really much. I just understand the statements that this theory was giving us this result and that theory was giving us another result. But what I wanted to say is that even though I don't understand a lot of theory here, I mean, what is exactly, where exactly the two-dimensionality, I mean, third dimension is used, because usually we just say that they are two-dimensional and we don't care about anything related to three dimensions or some effects that will not destroy this material, because actually there is a third dimension. That's for me a special theoretical direction to which I haven't ever tried to go, because there were a lot of other directions. But these are the top views of this materials. I also forgot what do we mean about the parameters, about the temperature and pressure. Oof, but I guess we just work in this. Oh no, I need to see, if I scroll too much, that gets us distracted. So in order not to scroll, I need to do like this and like this and like this, and then just click on the PDF. And unfortunately, the positioning is not so well done, but if we imagine that it appeared here, then we will be happy that you can open something just in one click. So I mean, always imagine this phase diagram, and here there is the question, at which part of this phase diagram we are working with in, but I don't remember the answer, so let's just skip this question. In some reasonable part. So if you ask me, I would vote for this part where there is a little, I mean, in this diagram, the lowest pressure and temperature around 100 Kelvin, for example. So this is the distribution of atoms on this lattice. So they are modulated, and this modulation can be also named charge density wave. And here, this article doesn't tell us anything about polarons, so we should think about this as just another word where another laws present. All these laws, they are around charge density wave, so no laws about polaronic physics is present. And okay, that's a big question which we're not going to discuss. Definitely how these two approaches coincide, and because one needs to work with it at least for a year, like this intensively, like I do past 2 or 3 weeks, to understand how this approach can be merged to one framework. So here we will dive into the world of charge density wave, and let's finally focus on the main information that this paper gives us. So that's the preview of the configuration of atoms of these materials. This is the Brillouin zone and the Fermi-surface that is put into Brillouin zone. And this stage I should, how to say, confess that I do not really understand well what happens here. I know the statements, but it's in my to-do list to work out this theory more. So the idea, as far as I understand, that like there are two, okay, the introduction to solid state physics is that, I try to explain the statement which I'm assured in, that there is a Brillouin zone and there's a Fermi-surface. So I tried to explain it more intuitively to tell what is really meant by this picture. So Brillouin zone, that's like, the idea that we can work with reciprocal space, because there was the story of diffraction where there was an incoming beam and there was reflected beam. And from that thing we got the Brillouin zone, but then suddenly when we were learning about electrons in solids, we used also some like Brillouin zone, they're always there. And this link is a little bit missing. I don't see this link yet, but these are two really well used and well-known statements, that somehow the Brillouin zone is in both places. So here, this is the Brillouin zone that tells us unique states of electrons in a periodic lattice. And this two-dimensional thing, so we can we can create copies of it and put all the copies around the whole reciprocal space. And the Fermi-surface assumes that we also live in a reciprocal space where there is momenta. So how does it look? I'm not sure. Maybe only these inner parts of these circles are the deformed Fermi sphere. Yeah, this is like deformed Fermi sphere, and the boundaries of Fermi sphere is the Fermi surface. So that's somehow it can work, but actually it's a really good question, which I thought about, but I didn't point it out as much as I could, that like why is and how. So here, that's the statement in which I'm assured that the Fermi surface is deformed, but I don't yet understand like deeply what is the reason why it is distorted so much. Okay, but I will just put this question to my list of questions and find it later. But that's what we are given, that this is the, how to call it, I don't know, but Fermi surface inside of the Brillouin zone. And there are some ideas how to relate this charge density wave that I have introduced to these properties of Fermi surface. But finally, as far as I remember, he wrote that this theory is not a good approach and it doesn't explain something that is really essential for these materials. But it will be way far in the future. This stream will not reach this point. We will just go through summary, introduction, and maybe some theoretical parts in the best way, in the best case. So the next plot that I have chosen as the main plots from this article is the band structures and spectral waves distribution in these three materials. So like if we do this ARPES, which I haven't explained yet what it is, then all electronic properties are about the spectra that we have like energy bands. If energy bands are, I mean, if electrons can easily go to energy bands, then we have a conductor. If they can't go, then we have an insulator. And there are some special points in this Brillouin zone in which directions we can measure the spectra. And I understand it very bad, unfortunately, because we're given these results, and that's more about experimentalists to understand these plots and like tell us if some model works or not. And theoreticians, they can work with derivations, with transformations of operators, and do not work enough with such plots. And that's my case, that I'm just aware that there are such energy bands. I'm just trying to explain that this is the direction along this side of this reciprocal space, and that's the one famous framework that is always used. So that's the standard things. If you speak with a professional, you cannot even comment all of this, but I assume that my viewers are people who just aware about physics and not experts. And it's also hard to be an expert in all the topics. So in these directions, these are the energy bands. And this color, black or gray color, it means the spectral weight. That's how I understand it. So suddenly on the one part of the energy band, you can have a lot of states. Another part, you can have very little states, number of states allowed. That's a typical result. So if we cool the system to the low temperature, then this thing changes. And I think that's the result from measurements. But I can be wrong because there are also calculations, but right now I think that that's the plot which was obtained from the measurement. It's interesting to know that all interest in physics is below the Fermi surface. And okay, I will just write this question. Yeah, that's an interesting feature, which is well known for people who work with such plots. But for me, it's an interesting question: why exactly E energy is lower than Fermi energy? Because we were saying that we have Fermi C, and all states are occupied under Fermi C, but here we have bands. Of course, there is no answer in this question, but maybe ChatGPT can give us the answer. And that's one plot that I have selected. Another plot is telling us also how the Fermi surface is changed if we cool the system. So at relatively high temperature, it was Fermi surface looked like this, and at lower temperature, it looks this way modified. So some gaps appear, and basically that's the only thing that happens. And this plot I can't comment right now because and also just note that these are all plots for different materials. So this is for tantalum disulfide, this is for tantalum diselenide, and that's for titanium diselenide. So I can guess that that's the main results for just different plots, but I need a moment for a pause. Okay, so the pause is finished. I wanted to just check one thing outside of my room. So these are the 3 different measurements for 3 different materials. They are collected one near another because Rossnagel collected them. So, and of course, plots of a different type. Okay, I have references to understand them deeper, but these are about basically electronic properties of these 3 materials. The bands, the Fermi-surface. It's actually interesting how to measure such a Fermi-surface, but it's not written there. And again, bands. But suddenly for this material we go through a different direction in our Brillouin zone. That's why there are L letters and also A. And it could be easy to understand if you just ask some AI assistant, but for this preparation I wasn't asking it, I was just thinking on my own and trying to understand on my own. And that's the second out of 2 basically main collection of plots in this article. So here there is a comparison of theoretical results about bands. So that looks like literally a magic how to get such prediction from at least something in theory. But these people who do DMFT or something else, it was written that they were state binding models. Yes, so here this article promotes us to use state binding models, but anyway, as far as I remember, he was taking these parameters of state binding models from DMFT, so it's not clear if we really can do something without DMFT. But anyway, that's the proposed theoretical result, that these are the energy bands. And again, for some reason, which experimentalists should really know well, we have this horizontal line which corresponds to directions in the Brillouin zone, and on vertical line we have the dispersion, so energy. Before phase transition there was just one energy band, and after phase transition this energy band changed drastically. So there are really a lot of bands, there are a lot of gaps, and I haven't yet reached the point to read about these gray areas. That's an important statement about the band structure. This is how it looks like from computations, and that's how the Fermi-surface looks from also computations, as far as I remember. But for me, it's still a miracle how they can calculate this, and that is very similar to this plot, which might be from experiments. And this is the preview of these letters that I was telling you about: A, L, and okay, there is also letter H, which is not here in the plots, at least I don't remember it. And here there are some different directions, as far as I understand. That's the only way I can relate plot C with plot A. Okay, but the idea is that if we go below the transitional temperature, then we have a very big change of the bands. So some new bands appear here and here, because like you see, that this part is the reflection of this part. So above phase transition, this will be exactly like this, but reflected symmetrically. But we are below phase transition, so suddenly there are such new bands. And currently I think that these are the 2 main collection of plots which describe us what is the experimental results, what are the theoretical predictions. And then there are a lot of discussions in the article about the theories and their features, but they are mostly in scope of references, so nothing is explained approximately. There are just citations, which is absolutely fine for this form of article, but it's not, of course, a good framework for understanding things. That's why I can again promote this focus structure tool, where we have a button, select PDFs for LaTeX extraction or import from archive, and you can click download first 5 articles, download first 20 site papers. So if you need, you can easily access these papers. But this app is not working right now, so no, right now you can't. But again, that's the motivation to do this whole project, to finally create a really useful app for science. So besides plots, I have selected also useful tables, which were used in some evaluations in the article and some derivations. So the table 4 is about theoretical parameters for these compounds, transition temperatures, some displacements, density of states. Zoom is not so smooth as I wanted. Density of states, resistivity. I still haven't reached that point of understanding to explain how important these values are, because I haven't used them ever, but maybe they can be useful. At least if you do like good theoretical work, you need some input parameters to test some models, like if a model can predict some property, or like if you want to calculate something for a particular material, you need to have some input. And maybe this table is a really good starting point for some inputs, but it's not explained in the article how we can use this table, for example. They just, I mean, they comment, Rossnagel writes something about it, but it's not like, hey, that's exactly an example of application of this table. So that requires additional work to understand it. But there are some discussions of this table, which I will go through later. Another table is present here where there are microscopic parameters. Here, these also microscopic parameters. But these are different ones: susceptibility, transition temperature, coupling, and energies. So for me, it's really a mystery how everything was, at least something was calculated here, but they have a lot of citations. So after I discuss all this article, I will try to understand some derivations of them. But on the level of this article, it's not really important to understand derivations. It's important to understand that in general, these are the properties that are in the interest. And these are the values, and you have references, so you can see more information about each of them. And there are some valuable comments which I will go through during reading the article. So that's the overview of what's going on in the article. So a discussion of these 3 materials, a presentation of experimental results, and discussion of theoretical calculations. Also a little background about the concept of charge density wave. And yeah, basically that's all. A lot of comments about applicability of theories, like typical review paper. But as you have seen from the beginning of the stream, this is a very well cited paper. 1000 citations, it's really a lot. I mean, and it doesn't mean that 1000 people have used it or read through all of these papers, but a lot of people read it and do not cite because they do some other research. So the impact of this paper is not a little one. Okay, let's just put some of these experimental results here for our reference, and let's start reading the paper itself. So that's what I have explained, that charge density wave is discussed here, but it's not from experimental point of view. Experimentalists it's from just reviewer, and yeah, like reviewer who focuses also a lot on experimental parts but do not focus on derivations. So here he writes basic models behind shared density wave formation, and the thing which I wrote here is that, okay, maybe it means that there are some excitonic. Let's look at this thing. So silic, we don't need to scroll much, we just need to scroll like this. And so here, that was the statement which confused me. So he said like different models, but the typical model which is still in my head is the parallel instability. And as far as I understand, there are several approaches to parallel instability. And I was thinking only about the approach from the Green's function point of view. Unfortunately, I haven't even understood the parallel instability really deep from different frameworks, but that's the typical thing that we say about shared density wave, that parallel instability occurs, and we have state of which is modulated. And if we have a modulation of a lattice, then there is the shared density wave, and it's also written here, CDW, shared density wave, periodic lattice distortions. So that's the two phenomena that happen simultaneously, and parallel stability for me always it was just about this. But here in the article they I'll just put it here. I'll just delete this question because I think it means exactly this thing, like different models. And what do we mean by models? And we mean that what if we have a different value of coupling? Then I tried to understand for several times what will be then, and he claims that if we have a strong coupling, then parallel instability is not, model of parallel instability is not applicable at all. And what do we need instead? That's not the thing I can answer you, but maybe that's what is meant here, basic models. So electron-phonon coupling with little coupling constant as the first model. Then what if we increase the coupling? And he writes, as far as I remember, that there are a lot of things that can happen, and it's a complicated question. So it's not clear what really happens, but the whole this picture of change of Fermi-surface is the one that he thinks that's most likely is not it's not true because it doesn't explain something. That's what I remember after reading this article. So some special features appear if we increase coupling. Then typically the shared density wave works for one-dimensional systems or quasi-one-dimensional systems. It's actually a good idea to know how the Fermi-surface looks. Yeah, so I will add this question to my list of questions. Because like typically we say that there are no one-dimensional materials, there are quasi-one-dimensional materials, and here we also have quasi-one-dimensional materials which are two-dimensional already, but if they are not so quasi-one-dimensional materials, so how would the real quasi-one-dimensional materials look like in this plot? Oh, let's get okay. I mean in this plot, how would it look like? But okay, that's the one thing that is another that gives us a path to other models. What if there are different dimensions? Another thing is that what if there are different bands, and then some holes can be there, some electrons can be, and some excitonic insulators can appear, and that's not the thing that I'm strong in. There are some, of course, links and statements, but for me, yeah, maybe I will go to this direction also, but right now for me that's just a peculiar direction. So these are the models behind chair density wave formation, which are basically generalization of the same model Paris instability. Yeah. And here it's written exactly what I have said, that experimental results, theoretical results are presented, and band structure is discussed. Also the spectral weights, which were okay. Let me better not comment right now about spectral weights, because maybe they are here, but I don't fully understand why exactly spectral weights are there, why they're needed. Maybe because of calculation of current, because current depends on how many electrons are there. So spectral weight gives us a direct impact to current. That's how my intuition tells me about it. But we need to check, of course, on this paper. And as it was announced, the tight binding model is the main thing here. And I will add some also formulas from tight binding model here. Yeah, it was explored indeed about unification of theoretical approaches, but by exploration, of course, I mean, based on my like view after reading this article, it was just a collection of statements of different effects and lack of current understanding, but it was indeed explored. And here, let me check. Yes, so here it's written that that model that is also labeled here as a mean field model. It's not the really great model, but I haven't reached understanding of why exactly it's not that great as it should be. Here it's also written like this: agree semi-quantitatively, but it means that there are some phenomena that they don't explain, and I don't know yet which are this phenomena that they don't explain. And yes, written that there is not one generally dominant factor. Of course, that's very intuitive, that if we have electronic systems, then there shouldn't be one generally dominant factor, because there are different materials and there are different factors in different materials. Some like coupling is stronger in one material, some coupling is weaker in another, or it's easier for electrons to jump from one material to another and from another to one. So that's very intuitive, but which exactly dominant factors can be, that's still a question, but I will explain it after I finish reading this article, or maybe during the stream I will understand this. And it was a lot of times written that they need to think again and develop a better model. Okay, let's just go to the summary and conclusion, which is the main takeaway from the article, and that will be the end of the stream, and next time we'll go through introduction. So the goal was to understand these materials. Was it achieved? Most likely no. I mean, or yes. Doesn't mean, it depends on what do we mean by understanding. Yeah, so okay, there is this canonical model of Paredes transition as well tell as I was telling you, and it was revised as we will see in the first part of theory. Um, but there is a strange generalization of whole the framework of electron-phonon interactions to the case of coupling of electrons and phonons where constant is momentum dependent. So it wasn't written in the article about the origin of such model because I haven't ever seen in any article before such generalization. But that's because, of course, I have seen very little articles, number of articles. But this theory is indeed discussed, and there are a lot of statements and a lot of cited literature. And these are the three materials that were in focus. So not so much was written about lattice distortion, energy gap, and Kohn anomaly. So it was written, which I will show you during next stream, that these are lattice distortions. Basically, I don't remember anything except these statements, and I also don't remember discussion of these errors. And maybe they mean exactly like errors here, that some atoms are attracted, but that looks like very not a periodic attraction. Oh, maybe it is a periodic actually. It looks like, okay, looks like a periodic, okay, but just drawn in a different way. Maybe the distortion is very little here. So that's everything what I know about the lattice distortion. The energy gap just appears and we can't do anything about it. And there are some links to some divergences of excitability, which will give us the appearance of energy gap. And there were several also energy gaps discussed, density wave gap, and I actually don't remember another one right now, but something was discussed. And nothing was discussed actually about Kohn anomaly. I mean, there is divergence of excitability, yes, but I mean, the derivation was not there, and the typical plots for Kohn anomaly is also not seen in this article, but definitely it's in the cited articles. So somehow they get this conclusion that there should be a intermediate or strong coupling. And let's just postpone this question to understand why exactly like this. The statement is very clear that there is the effect and there is the model. And in this model, there should be a strong coupling to or intermediate coupling to explain this effect. But that's an important statement actually, because typically, let's see what's here. Typically, we are given this model of peerless transition, and it's a one-dimensional model, but no one was focused. I mean, I haven't seen any person who was really bothered of one-dimensionality about this model, because we typically say that, hey, in two-dimensional case, it will also work, but you need to have quasi-one-dimensional materials or this Fermi-surface nesting that we will go through. So seems that in conclusion, they say that no, that's not the case, and this model just doesn't work at all for I mean, works very bad to some little extent semi-quantitatively. It explains some observations, but also it's very important to understand which exactly observations, and we will go through it very later. And that's important statement that if we speak about this model, then we should not really hope that it will be very relevant to a transitional metal Dichalcogenides. But, oh, by the way, that's the Kohn anomaly that was just mentioned here, that the frequency goes suddenly to 0 of phonons. But that's a schematic illustration, and what I really wanted to see is some real experimental consequences of this effect. That's what I haven't heard yet about. Yeah, here they say, I mean, that's too complicated sentence. They could have, Rossnagel could have written that he was looking at ARPES results on both phases. Yeah. So I don't know any real uncertainties about the gap. Uncertainties. Yeah. Yes. So basically, they just looked at ARPES. That's what I have shown you already. And I don't think that it helps somehow resolve any uncertainties because it was written that it's hard to determine. For example, excitonic gap. Yeah, I was not sure that which gaps are there, but I was announcing you that there are these several models that are proposed, and this excitonic accelerator model is also there, and it also has a gap, so there are some unclear comments about these both gaps because they are, as it's written, undistinguishable, but okay. Okay, let's continue. So as far as I understand, here it's written that these are the plots. Of course, these are not the only plots, but I have chosen them as a typical plots. So these are the plots from ARPES, and this is the plots from Tate-Binding models. So Tate-Binding models work. It's actually a good idea. What are the parameters of Tate-Binding models? I will add this to my first part later. I also got the idea that if we develop this app, we can put somewhere here for quick notes. How did I write it? Okay. Improv app. Yeah, it will be better than using like this Notepad++, but Notepad is reliable and this app is in development, so it's better to use Notepad++. Okay, let's read what they write here. Yes, as I said, this plot is really similar to this plot. That's why the Tate-Binding model works. Okay, that's a very like a statement that we should think more because it tells us something that I wasn't thinking on my own. So that's like a very strange statement because I mean the standard theory that was even revised in this article, they said that there is a parallelist model and all this theory about electron-phonon coupling. Right now I think about this Green's function approach because that's the only approach I know about the parallelist transition, and I can make a stream actually about just this approach, that we calculate Phonon Green's function, then we get the divergence. Actually, I can even open you the derivation of it, which I imagine, but fortunately it's not in my notes. This is, I mean, it's in my notes, but it's way easier to just scroll through this original paper where I took this note. So if you don't understand this language, it doesn't matter. It's written like here, parallels effect and mean field theory. That's why also in this article we have a lot of mentioning of mean field theory. And we use just basically the same Fröhlich model of electrons and phonons, but for one-dimensional case. And for this case, we also have a substitution, which makes a lot of sense from intuitional point of view, but it's not a theory, so I'll better not comment this. And somehow you get also the formula for the interaction potential. So that's why after simplifying Hamiltonian, you can get eigenvalues and get that there is a gap and divergence at one vector. And I will definitely go through this theory again because that reminds me a lot of things from this article. Let's not check it right now, but this formula looks very familiar for me from the article. And also, so here there's actually a good theory, but it's explained very insufficient. I remember I was trying to go through this theory 2 times in my life, and I just abandoned this. It was not clear, and that's game over. Aha, that's the actually derivation that I imagine approximately, that we calculate the Green's function for phonons. To do this, we need the polarization operator, and the whole formalism already provides us with the general expression, and what we need is to do some very advanced simplification of this equation, but that's just purely mathematics. So in general, in this formalism, we basically have this equation, and then we do another transformation, and then we use this property that we need the divergence of the Green's function of phonons. And from the divergence, and after another advanced mathematics, we get the equation for the frequency. And that's exactly this frequency that's here. That's the Kohn anomaly. And here we also see this Kohn anomaly. The thing is that here we have divergences at 2p Fermi. And here I need to check about this. And also before I saw something about divergence somewhere. Okay, maybe it's always about 2k Fermi. Yeah, it should be always about 2 Fermi momentum. Maybe it coincides to this plot, but that's a little problem that I wasn't thinking really a lot about it. So let's go back to this question. So here they say that from gap. Yeah, so they say basically that all this model is not really applicable, and I don't think that they will say that that's the wrong model, because for some other materials it should be applicable. That's what I heard. Never checked, but that's a well-known thing that at least somewhere this is applicable. But here they say that that's not the case, and the real reason is that there are some sub-bud splitting and shifts over extended part. So I haven't reached that part of article that's connected to this conclusion. So what is the sub-bud splitting? I can only guess, but we have seen the main picture, and that's the splitting of subbands, I guess. So also need to check that there are a lot of divergences, I mean, on the 7. So, I mean, not divergences, the degeneration on the 7a picture. I'll check it. And that's how I understand it, sub-bias splitting, but also the shifts. So that's an important really result, which tells us a lot of about theoretical approach to charge density wave of this material. So they say that whole parallel theory is basically not the one that it's worth of application. Okay, another statement which is really very important is that they started, as far as I understand, like setup is to start and started to explain using weak coupling and strong coupling mean field models. So there is indeed a big discussion of the approaches, but I don't yet understand this mean field model, how we can, I mean, you can just plug a different coupling. I still, because that's the problem that I was learning charge density wave from this theory, and in this theory, it seems that we just do the transformation, and what's the problem? Like we don't, nothing is written about the, okay, maybe I missed it. Maybe I should go again through this theory, but I don't remember any place where we have a limitation of the coupling constant. And also, I'm very familiar with the theory of polarons, where they say, yeah, let's just use the electron-phonon interaction for intermediate coupling, not for all intermediate couplings, but for some intermediate couplings, and we just do another transformation and get some models, but it's very far from this article, so I can't connect that theory with these experimental observations. But okay, the statement here is that they tried two different mean field models, which should be somewhere similar, and it's interesting to note what is the difference between them besides the value of coupling. Like maybe there are different transformations, or at all like different frameworks. Like in unified way, it means that we should start with one formula, but don't remember any one formula that we start from. But they tried to do it to discuss theory, and we will just go through theory and understand it. And again, they state this statement that there is not a good explanation of experiments, which I don't know, but we will see it in the article. And they repeat again this statement that prediction of let's say results do not coincide well with experiments. They paraphrase something from the abstract which we have discussed. There are some mosquitoes, so I need to be a little bit distracted. Okay, let's go again. Okay, then they again paraphrase that they can't describe experiments well. So we have encountered this statement already fourth time. Nothing much to comment here. And k-independent interactions, it means that the coupling constant should be a constant or k-dependent value. Yeah, so, but I'm not familiar with this theory. I need to go through electron-phonon interactions to understand what is the origin of this k-dependent interactions. But this theory doesn't work. That's what we clearly understand after a lot of statements about it, even after the first statement about it. And again, the same statement that we need to think more about it. Then, in scope of his theories, he somehow really wants to have k-dependent interaction, because maybe he found some reasons for such interactions to be important, and 3D Fermi-surface is not the thing to understand. If we have two-dimensional model, maybe he means that two-dimensional model is not enough and we definitely need a three-dimensional model. But that's also a strange statement, which we will think about during reading the article. And again, they write the same, that they need to think about this theory more and work out it more. And they say that ARPES should confirm the theory, but I think that's already done. I don't know what shouldn't be done. That's my comment here. Okay, here they say they mention time resolved ARPES, but it's like advanced ARPES. So if you use some really advanced model about this material, then maybe you can predict some time dependent phenomena and use time resolved ARPES. We remember from the stream before the last one. Sorry, I wasn't scrolling to the wrong side. So here we have also time-dependent phenomena, but that's not a femtosecond phenomena. That's a phenomena during like 10 minutes or 20 minutes. So here they speak about something different, and this domain wall reconfiguration goes way beyond of what's written here. Because maybe that's called a hidden phase, and here we don't have at all discussion of this hidden phase. So if we have such domains, that basically that's approximately a definition of a hidden phase. And they think that it's possible to do. So the conclusion tells us two these main statements, which are not explained, of course, but we need to read the article to understand them. And other rest part of the conclusion is a repetition of the abstract and another strange but not really important statements, which can be skipped. That's how I see the conclusion. Okay, let's just go through the introduction, and that will be the end of the stream today, because definitely it's a bad idea to do it for a long time. And actually nothing is really complicated here. Here there is just introduction to charge density waves. Yeah, that's an old question. I mean, I'm not an expert in theory, that's why I posted the question, when was it discovered? If you really want, you can ask ChatGPT, for example, but that's not the thing to, like, I mean, it doesn't worth it to focus on it. Yeah, basically people started thinking about it. And we still don't understand much about it. And that's the confusing statement that parallel instability, cone anomaly, and we need to forget the word giant because we don't know anything related to giantness. And also, it's not really, I mean, I don't know, like we can just think about cone anomaly. I'm sure that nothing will be bad if we forget the word giant. And Young-Taylor effect, band Young-Taylor effect. Of course, I'm not an expert, but right now I think it's also not a standard effect, but some exotic view of some things that happens in bands, but maybe we will maybe I will read once article about it, but right now I think that's better to forget because that's analogy from molecules. But here we don't have molecules, so anyway, that's just an analogy, and we need to know some formula behind it, and it's a low priority effect. And excitonic insulator is the one that will be discussed below. And that's actually a bad sentence because there are different origins of these effects, and these are not basically yeah, like some aspects, but this is just different effects. That's the collection of effects, so it's better to not focus on this sentence. The idea is that there are different effects. And again, they say that it's not done, but there is strange citation, which there is no sense for us to click on and just be distracted from what's written here. Then they here cite what it so they say that this chernecity wave of the standard theory is, and I have already wrote myself. No, I didn't. Okay, I will add this to the first part, not to scroll like this, but to do it faster. So here in the theory that we will go through, it's actually right here. That's already the standard theory, and we will go through it during next stream. So here they say that this theory, let's open these images for you to become more familiar with them. So you imagine this modulation of electrons, modulation of a lattice, they coincide and there is a gap for electrons. These are the typical statements in scope of this theory. So here they cite that this explains, as I said, quasi-dimensional solids and also some two-dimensional systems. And it's really good idea to check these references. Or I mean, yeah, to understand, I mean, not just check, but to understand how it is really describes this well. This is just a good references. Okay, then here they write again the same, Rossnagel writes again the same statement that was before, that they should think again. So you see that this article could be even less in the material because a lot of statements just repeat each other in different form. Yeah, so here, I mean, that's also a useless actually statement because yes, there are different charge density waves, they will be discussed, but okay, they could just discuss it and that's all. It's not an important statement. There are, yeah. I don't know which these three distinct charge density wave they mean. Commensurate charge density wave, non-commensurate, nearly incommensurate, but there are really a lot of them, like you can see here. Okay, there is no why there is actually no incommensurate charge density wave. Okay, I don't know this answer because that's why I wasn't also thinking about incommensurate charge density wave. I was familiar only with this non-commensurate and commensurate, and that's all basically. And superconductivity is maybe something of this or this. Not so much comments are given here about the structure superconductivity. Maybe if we look at this plot, then it will be a chernivtsi wave and superconductivity at the same time. So, and they don't expel one another. But okay, we can forget this sentence. Nothing is really useful here. And here also, by the way, the comment, there is some dynamics. They said before that some femtosecond ARPES can be used, so maybe dynamics can be used for them, for that effect, but that's like really complicated effect. Even this typical chernivtsi wave, static one, it's not easy effect at all. So I will not discuss some parts of it, which is very expected, right? I could also not write this. Like, I mean, in the article on the origin of chernivtsi wave, nothing is written about dynamics and here, so sorry, where is it? Yeah, superconductivity. So that's also what we expected. Nothing is really important here. Yeah, and I mean, that's what also written here, that they focus on these materials, but for some unknown reason they cite other materials which will be not dealt with. So that's the useless citation. Like, I cite this paper and I'm not going to use this paper. But okay, we know that there are some chernivtsi wave materials, so maybe once I will open also these articles. Yeah, and that's again introduction to what I have said before, that there are ARPES results and there is a tight binding model. Which will be used to explain ARPES results. And here there is again a clear statement. They will, let's find the verb, focus on interpretation, experimental results, applications. Focus on resulting implications for a microscopic mechanism. There is no implication for resulting microscopic mechanism. It's just like a general activity for finding the finding the right model for chernivtsi wave. Yeah, so that's how you should understand the statement. You can't use. Oh, yeah, finally killed mosquito. You can't use the like results for implications for microscopic mechanism, because I mean implications. Okay, I mean it doesn't matter. It's like a question about phrases. The idea is that they will try to use these results to get some microscopic model, but as far as I remember, there are just discussions and nothing except references, discussions, and collections of effects which could maybe potentially influence. So that's what happens when people work without a focus structure tool, because if they were working with focus structure tool, they would collect all the formulas. It would be 100 document of just this collection. I mean, the original papers would be, let's say, 10,000 pages, and the collection would be for 100 pages, and he would be thinking about derivation, not about this summary without like formulas. So it's right now additional work for me to extract the formulas that I meant here, which were tried to explain the ARPES results. Here they say that they will be dealing with this mean field model, but it's also a confusing statement because before they said that that's not a good model. Maybe they, as far as I remember, nothing is done about the good model except very valuable comments and citations. But here, indeed, all what is done is the discussion of like just mean field models. Yeah, and you need to plug some parameters there, so it's not really clear how these parameters enter the model, and we will see in the theoretical part that in all this part, like Pearson stability, weak coupling, one dimensional, so it's not clear where to put exactly these parameters, but it's written here that only these models will be used, so real model will be not developed, it will be just discussed. That's how I understand this sentence. That's also a useless sentence. He was writing it in the abstract that he considered this approach as experimentalist, and he points out weak points in our understanding. I, unfortunately, after reading 70% of this article, didn't understand where are the weak points, but during this stream, during next stream, I will understand. The stream will end after this several sentences. But nothing is complicated here and worth of our discussion. They just say that we'll summarize the idea. What's next? Yes, they will focus on models that are used. Then they will discuss experimental results. And they then at the part 4, section 4, they will explain the results by band structure calculation. And I haven't reached part 4, unfortunately, but I will reach it tomorrow. And as was said before, they really stick to the tight binding model. So in general, like see here, it's written the working hypothesis mean field model, and here they say they will use tight binding model. So again, it's not clear. I don't know why did he write it like this. The idea is that yes, there is discussion of a model of electron-phonon interaction, which he calls mean field model. I mean, still open question for me, what is exactly a mean field there, but okay, that's well known as the mean field model. I will just write here, reminder for myself. Okay. I will just revise this Paredes effect. So right now we suddenly he said to us that he told us that the tight binding models are the main model. So what is the real option? I mean, that's the bad question because both type of models are discussed, and here he says that he will deal a lot with tight binding models because these are the best models he thinks of. There are DMFT models, but he thinks that they are very unintuitive. So that's why he will just, that's what I remember based on first 10 or 20, okay, maybe 10 or 15 pages that he said that we will just map the results of DMFT to the tight binding model. So this is the second type of model which will be considered. And then there are at least 3 pages of discussion why there are these distortions of the transitional metal dichalcogenides. Why it is so, I don't know, because I haven't reached that part, but maybe there are just speculations and not the given answer. So, to conclude, that we have some experimental results which are not really explained, were not well explained during this stream, but we will discuss them during maybe one stream after the next. There are other results, experimental results, that there are some distortions of the lattice and this strange change of this Fermi-surface inside of the Brillouin zone. And there are a promising tight-binding approach that maybe coincides with this announced mean field theory standard approach to some extent, but we will see a discussion about this approach later. Also, we have some tables, at least two, maybe more, where there are parameters which are obtained parameters, so it's actually a good thing to play with, but you need to be a master of physics to do it, to see like, hey, we have this parameter, what if I derive this parameter from this model? Or check that this parameter is here, I mean, that indeed this parameter is so, or it can be driven somewhere, or use a model that derives this parameter and try this model to derive this parameter. So that's a good playground for theoreticians. And everything starts with really careful understanding of this article. And we have done introduction and summary, so it's like one page, 2 pages, 3 pages, 3.5 pages. That's our path, pace. So if I click Control, yeah, I misclicked. I still forget this hotkeys which I have chosen. So thank you for the stream. That's just the first part. It taught me some insights. How many insights? Okay, that's not a little number of insights which I got that was available time for me. Also, I want to conclude that it's really hard to do science because and to speak with someone and you see that discussion takes really a lot of time, and it's very hard. It's nearly impossible to find someone to discuss all of it with. So such stream is the best option I know to really be motivated constantly, not to burn out, not to be unfocused. So I'm really happy that I have the streams. So thank you for future watching of the streams and see you tomorrow, I guess, because tomorrow will be a second part. Bye bye.